this duality. This is normally called ADS-FT duality. Okay. So to understand this duality, let's first understand the object in this relation. Okay. So let me just say a little bit about the object in this relation. First, let me say a little bit about anti-de Sitter space. Since the since that may not be something you have worked before. Okay. So one way to write.
طبعا انتي دي سيتر سبيس بناء على الفيديو السابق. انتي دي سيتر سبيس لديه الخواص التالية. هذه الخواص بناء على نظرية يوسف، ليس بناء على ما سيقوله المحاضر، إنما بناء على نظرية يوسف يمكننا التنبؤ بأنتي دي سيتر سبيس كيف يكون. طيب، أنتي دي سيتر سبيس يكون كالآتي: في الثقب الأسود لديه خاصية أن على الحدود أو على أفق الحدث فإن الزمن يكون، يعني إذا كان الزمن أو الملاحظ إذا كان يقف على الحدود أفق الحدث ويرى في الداخل، يرى أن الزمن يتقلص داخلا أو ما يسمى بالتايم كونتراكشن، مثل الإنسان الذي يقف على سطح الأرض ويرى الذرات والجزيئات، يرى الأحداث هناك سريعة جدا، وبالتالي داخل أفق الحدث يرى الأحداث سريعة جدا. وإذا دخل إلى داخل أفق الحدث داخل الثقب الأسود يرى ماذا؟ يرى الأحداث بالخلف بطيئة جدا، وبالتالي هو يذهب إلى المستقبل الأحداث. طبعا هذا الأمر شرحته في فيديوهات كثيرة، وليس فيديو واحد أو اثنين، فيديوهات كثيرة. طيب، ماذا يحدث؟ طبعا هو ليس الزمان فقط، الزمان والمكان الاثنان مع بعض. طيب، ماذا يحدث في هذه الحالة؟ في هذه الحالة نجد أن الذرات أو الجسيمات تضعف، طاقتها تقل. طبعا هذه من معادلة الطاقة التي ذكرناها في الفيديو السابق. الفيديو السابق مهم جدا. الكتلة تضعف، الطاقة الكهرومغناطيسية تضعف، وبالتالي هذه الجسيمات تضعف، تقل حتى تصبح مثل السترينج، أو يمكن تمثيلها بالسترينج. لا تصبح مثلها، لكن يمكن تمثيلها بالخيوط. وهذه الخيوط، الفيزياء التي تتحكم فيها هذه الخيوط تتحكم تشابه تماما الفيزياء التي تكون على الحدود. على الحدود أقصد على ماذا؟ على أفق الحدث. يعني الكومبنسيشن أو نقول المقايضة، بأنه الفضاء على أفق الحدث إذا كان نريد أن الفضاء مشابه له داخل عميق في الثقب الأسود، يجب أن نصغر الأبعاد بتاعت أبعاد الجسيمات المتفاعلة. وبالتالي نجد أن الأنتي دي سيتر سبيس لديه الخواص التالية: أن في الباوندريز اللي هو في الزمن ما لا نهاية، نجد أن يساوي الأحداث التي في الزمن ما لا نهاية تتحكم فيها ما يسمى بكيو اف تي، اللي هو مخططات فايمان وتفاعلات الجسيمات الأولية وهكذا، أو ميكانيك الكم. وعميقا داخلا إذا أردنا فضاء مشابه لهذا الفضاء الخارجي، يجب أن، ونظرنا عميقا، يجب أن نصغر الأبعاد حتى نصل مرحلة السترينجز. وبالتالي السترينجز، الفيزياء التي تتحكم في السترينجز هي نفسها الفيزياء التي تتحكم في الفضاء على الباوندريز. هذا هو فضاء أنتي دي سيتر، لا شيء آخر. لا شيء آخر عن طريق نظرية يوسف. وسيتحدث عن فضاء انترديسيتر وسيخبرنا بكثير من المصطلحات والمتغيرات وأشياء غريبة جدا جدا نراها، لكن هذا هو الفهم العام لفضاء انترديسيتر عن طريق نظرية يوسف. موضوع بسيط جدا جدا. الجسيمات صغرت داخل الأبعاد، داخل عميقة داخل الثقب الأسود، يصغر معها التفاعلات وتصغر معها طاقات الوضع وتزيد طاقات الحركة وطاقات الأجرام تزيد وينقص التفاعلات يعني الجي اس الكوبلينج كونستانت يكون قريبة من الزيرو، وهكذا الأبعاد تكون قريبة من الزيرو والكوبلينج كونستانت تكون أو ثابت الارتباطات يكون قريب من الزيرو، وبالتالي يمكن تشابه ذلك الفضاء بالفضاء على الحدود أو على أفق الحدث للثقب الأسود، والتي تتحكم فيها مخططات فايمون وتفاعلات الجسيمات الأولية من إلكترونات وبروتونات وما إلى ذلك، كواركات وما إلى ذلك. فقط هذا هو فضاء انترديسيتر. طيب تعالوا نذهب ونرى هذه التعقيدات وهذه الأمور حتى يصل لنفس النتيجة التي وصلت إليها أنا.
The metric is this metric. So this is ADS5. So this is ADS5. Okay. So this is ADS5 metric. You can actually write it as ADS. Yeah, let me just copy it down. So you can generalize to any number of dimensions. You can generalize to any number of dimensions. If you make this part into a d-dimensional Minkowski space-time, okay, and then this would be the metric of ADS, say d plus 1 dimension. So this is a d plus 1 dimension Minkowski. Then you have another r direction. So let me call this my. So now let me relabel this to be 1. Okay. So r can be considered as a curvature radius of this space-time. So this r is a constant, and this radius r goes from 0 to infinity. Okay. R goes 0 from infinity. So roughly, a geometric picture here is that. So you can see that you have a half space. Okay, you have a half space r from 0 to infinity, and at each value of r, there's a Minkowski space-time. There's a d-dimensional Minkowski space-time. So if you fix r, then you just get some d-dimensional Minkowski space-time, and with some prefactor to define the scale of the Minkowski space. Okay, so just like this, you have a half line r from 0 to infinity. Then at each point of this half line, is foliated by d-dimensional Minkowski space-time. So that's essentially what this does. So the key thing is that the Minkowski time is what we normally call the warped. Is that the scale factor of this Minkowski space-time depends on where you sit in the radial direction. Okay, so this r we normally call radial direction. That depends on where you sit in the radial direction. So when r goes to infinity, at r goes to infinity, the scale size become infinite. So this we normally call it to be the boundary. So this we call to be the boundary. Say I equal to infinity, we call to be the boundary of the space-time. So this is similar to say when we write the Euclidean metric in this form. When r goes to infinity, the sphere size becomes infinite, and then this is essentially the space-time boundary, roughly. And so this can be similarly understood. Okay. So this ADS is a space-time ADS is a space-time of constant curvature, constant negative curvature. Okay. In fact, this is the most symmetric space-time of negative constant curvature. So you can easily check. This satisfies the Einstein equation with the negative cosmological constant. So you can easily check it satisfies the Einstein equation. So now because now I'm using this R denote this radius, this curvature radius. So now I will call my curvature tensor always using the script now. So also Mn now refers to all directions in this ADS. So you can easily check it satisfies this Einstein equation with some cosmological constant. And you can just compute it's easy to compute the curvature of this guy. So let me just write down the answer. So first you can you can compute the curvature of this guy. You can just find the answer. You find the curvature, the rich scalar is given by minus d times d plus 1 r squared. Okay. So this is a rich scalar. This r is the same as this is r. And similarly, you find the cosmological constant. Then you can find here from the is given by minus 1/2 d minus 1 divided by r squared. Sorry, here should be minus 2. Okay. And I said that this is the most symmetric, homogeneous.
طبعا هذا الأمر غريب جدا. أنا أول مرة ألاحظ له الثابت الكوني يساوي نص دي مضروب في دي ناقص 1 على ار تربيع. انظر إلى التشابه بين الكيرفاتشر والكوزمولوجيكال كونستانت. يعني هنا على ار تربيع، وهنا علامة الناقص، وهنا على ار تربيع وعلامة الناقص. والاختلاف في أن دي هنا دي ناقص 1 وهنا دي زائد 1. وبالتالي الثابت الكوني أقل من الكيرفاتشر ببعد. لكن أنا لا أريد هذا. أنا أريد شيئا في غاية الأهمية، وهو أن الثابت الكوني يتناسب مع R أو يشابه R. وأنا في سلسلة نسبية العام علم الكونيات افترضت هذا تماما، أن الثابت الكوني يتناسب مع الكتلة اللي هو ordinary matter mass. وحسبت أن الكيرفاتشر في معادلة فريدمان يمكنكم الذهاب إليها. فحسبت أن الكيرفاتشر هي جزء من الكتلة mass density، وبالتالي الثابت الكوني لا بد له أن يتساوى مع المادة والكيرفاتشر مع بعض، وحتى أن الإشعاع أدخلته مع المادة. بالتالي الثابت الكوني لا بد أن يتساوى مع المادة والإشعاع والكيرفاتشر أو الانحناء كلهم مع بعض. هنا شيء غريب. هنا في دي سيتا أنتي دي سيتا سبيس نجد أن هذا التشابه الكبير بين الثابت الكوني وبين R الكيرفاتشر. طبعا هنا الكتلة يعوض عنها بكيرفاتشر، الكتلة أو الطاقة يعوض عنها بكيرفاتشر. فهنا التساوي بين أو التقارب أو التناسب، دعنا نقول التناسب بين الثابت الكوني والكيرفاتشر. هذا يعطينا تشابه كبير فيما ذهبت إليه أنا في السلسلة السابقة. يعني شيء غريب جدا. يعني ما عدا الحد الذي يمثل دي زائد واحد ودي ناقص واحد. لكن هناك تشابه كبير جدا، يعني هذا واحد على ار سكوير وهذا واحد على ار سكوير، شيء غريب جدا جدا يعني. يا دوب لاحظت هذا الأمر يعني في المسحة السابقة لم ألاحظه، فهذا يؤكد ما ذهبت إليه في السلسلة السابقة.
Okay. And I said that this is the most symmetric, homogeneous, negative curvature space-time. So this is reflected in that actually you can write the Riemann tensor. The Riemann tensor of this space-time purely in terms of this metric itself, without using derivative. Okay, so this is essentially the definition of the most symmetric negative curvature space-time. Is that the Riemann tensor can be written solely in terms of metric itself. Okay.
طبعا هذه الخطوة أيضا تحدثت عنها في السلسلة السابقة، أن في اشتقاق معادلة فريدمان من الاشتقاق معادلة فريدمان إنه يعوض المعادلة كما هي دون اشتقاق. اذهبوا للسلسلة السابقة ستجدون هذا الأمر، شيء غريب.
So these are just some facts of this space. So we often use a lot of coordinates. Sometimes it's often convenient to use, instead of using this r, we will introduce another coordinate. You introduce a z equal to r squared divided by capital R squared divided by small r, essentially just the 1 over r. And because the capital R goes from 0 to infinity, then small z also goes from 0 to infinity. But now the boundary, z equal to 0 is the boundary. Rather than z equal to infinity. And then the metric can be written in a slightly different way in terms of these z coordinates. Can be written in this form, okay? You can see it easily. So again here, you just change the label r by z, and now z equal to 0 is the boundary. And going to interior corresponds to increase z. So d corresponding to in the different direction. Okay?
Should you say in order to derive this ATS metric, we already assume the small r approach to 0?
Yeah.
But here it tends to infinity?
Yeah. That's a very good question. I'm waiting for some of you to ask. So this is the the physicist magic, which we described. Yeah, this is the physicist magic. So yeah, let me just say this way. So you have infinite throat. So we going to lower energy limit, we should just go very much down in the throat, okay? But once you go down once you decouple those discrete freedom, then you can just rescale your energy scale. whatever you want. Whatever you want. You go to finite energy, etc. And as far as you are in the ADS5. As far, yeah. Once you decouple those things, then you are living in ADS. Then you are living in the ADS, and then you can talk about the energy scale or any radius as you want. Just become relative to itself. You see what I mean?
Is that kind of normalization?
No, this is not normalization. This is just say when we take the low energy limit. The reason we take the low energy limit is we want to decouple those massive modes. And once we decouple those massive modes, and then we consider the finite energy. And when we consider the finite energy, because we consider finite energy relative to the low, we still consider a finite range of energy. It's the same thing as that. Is this clear to everybody? This is a very important point. Yeah. Good. Yeah. The question is that previously, in order to decouple those high energy modes, when we take the low energy limit, we have to take R equal to 0. So why here we are worried about R go to infinity, R equal to infinity here? Okay. Why are we worried about R equal to infinity? It seems like this is going outside our previous regime. But the answer is that once we decouple those high energy modes, then you can just extend the energy to whatever energy range you want, because you have served the purpose of decouple those. Yeah, because those things already went to infinity. Don't have to worry about them. Yeah, is it clear? Just like in the Yang-Mills theory, we say we take the low energy limit to decouple those massive modes, but eventually in the Yang-Mills theory, we will consider very high energy process in the Yang-Mills theory. Okay, but those things we decouple have even higher energy scale. Okay. Good. So we call this is this is 1, this is 2. So in fact, actually 1 and 2, they are not covering the full anti-de Sitter space-time. So actually, they only cover a part of anti-de Sitter space-time. So they only cover, say, what is so-called a Poincare patch, a patch of de Sitter space-time, anti-de Sitter space-time. So now let me just mention a little bit what is normally called the global ADS. Okay. So the ADS or global ADS. So so let me first write down the sentence. So 1 and 2, 1 or 2, only covers a part of full ADS. Okay. So the global ADS, the so-called global ADS, can be defined, can be described as a hyperboloid in the Lorentz space-time. Okay, hyperboloid in Minkowski, in D plus 2, the Minkowski space-time of signature 2, D. Okay, so to make this precise, say for example, if you go to the GR book, for example, the book by Hawking and Alice, called the large-scale structure of space-time, the way they define the anti-de Sitter is as follows. So you consider a D plus 2-dimensional Minkowski space-time with signature 2, D. So you consider a Minkowski space-time like this. Okay, so now you have D positive signature and 2 negative signature. So X starts from -1 index to 0, which gives you the negative signature, and then you have, so this is the Minkowski space-time of the 2, D signature. So now you consider the following hypersurface in that space-time. Okay. So this is a hyperboloid in that space-time, and this defines your ADS. Okay, so this surface defines ADS. Okay, this surface defines ADS. So of course, this is a very different way to parameterize parameterize ADS than either this metric or that metric. And you can actually parameterize ADS in many, many different ways. So now let me just mention a few ways to a few choice of different coordinates to parameterize these hyperboloids. Okay. So the first is what one is called the Poincare coordinates. It's this one. So first is what we call the Poincare coordinates. So in this Poincare coordinates, you introduce R. So R there is given by x minus 1 plus xd. So you take the one of the negative signature and the one of the positive signature. You take x minus 1, xd, you add them together. So this is like some kind of night cone. And then you write x mu. So there we always write x mu equal to Tx. Okay, so this is a d-dimensional Minkowski coordinate. You add x mu equal to r times capital mu divided by r. Okay. So in this hyperboloid, you make this definition, and then you restrict to the region of r greater than 0. Then you recover. So 1 corresponds to r greater than 0 part of this metric, okay, of this space-time. And you can easily check yourself. Just make this definition. This is the exercise you should do, which I don't have time to do here. Just plug this in, plug this into that metric, plug this parameterization into that metric, and then you find you will recover 1. And 1 will correspond. 1 is only restricted to r equal to 0 to infinity, so you only restrict to the r greater than 0 part of this. And if you just introduce this in principle, of course, r can be smaller than 0. Okay. So these are Poincare coordinates. So once you go to that metric, then go to this metric, just it's the same. Then also let me describe something called the global coordinates. So this is by notice the following structure. So this is have the form of the two, the difference of two squares. So I can write, so let's write x I to 1 to d xi square to be some function r square and r square times r square. So this r have nothing to do with that r now. Now we are doing a different set of coordinates. I'm just using the same notation for convenience. So let's introduce a new coordinate r, which is just the sum of all these square. And then I introduce, then from this equation, the x1 minus x0 square should be equal to r square plus 1 times r square. Okay? So now I can. So this is a circle. So for fixed r, this is a circle. For fixed r, this is a d minus 1 dimensional sphere. Okay. So I can introduce the d minus 1 spherical coordinates on this, and introduce a circular coordinate on this. Okay. So if I do that, so let me just call the circular coordinate on here tau, the polar coordinate in the x minus y, polar coordinate in the x minus 1 and x0 plane. So let me call this tau, and let me call the a spherical coordinate here omega minus 1, omega d minus 1. Okay. Then you plug this into here. Then you find the following metric. So you find the following metric. You find ds square equal to r square minus 1 plus r square d tau square plus dr square plus 1 plus r square plus r square d omega d minus 1 square. Okay. So remember, tau is the polar coordinate in this x minus 1 and x0 plane, and omega d minus 1 is the polar coordinate in the x1 to xt. Okay? And then you get this. Again, it's an exercise you should go through yourself. Yes?
So one question, so I'm just trying to visualize this. So there's these, I mean, at least the way it works in RM, I imagine. So you have these two sheets which are like disjoint from each other.
Right.
So how is it that this enables us to go smoothly between them? Like it seems that there's, so maybe I'm confused about what you did.
Sure, what do you mean?
So we're trying to describe this object which has two disjoint components.
We only look at one component.
So what's the point of global coordinates? Is it just a different?
No. That only covers part of the one component.
Oh, I see. Okay. Yes.
Yeah. Yeah. Okay, good. So you look at here. Yeah. So that's the again r, where it goes from 0 to infinity, but this r is very different from this r now. Okay. So in this definition, tau is a polar coordinate. So in this definition, tau will go from 0 to 2 pi. Okay. But once you write it in this form, nothing depends on tau. So you can extend tau to any range you want. So once we write this form, we take tau, goes to minus infinity to plus infinity. So this is our generating time, rather than from 0 to 2 pi, we take tau from minus infinity to plus infinity. So sometimes this is also called extended ADS. Sometimes people don't just bother to do that. You just extend it automatically. Okay. So strictly speaking, this, as a definition of ADS, only corresponding to the part of tau from 0 to 2 pi. Okay. And when you extend tau from minus infinity to plus infinity, you actually have an infinite copy of this. Okay, so now with one more thing, we can. So this coordinate is nice. Now it covers everything. Covers everything, but even actually a little bit more, because you have now you extend the tau to minus infinity to infinity. We can visualize this metric a little bit better by doing the following a larger transformation. So now let's take. Yeah. Before so that let me say a few words about. Yeah. Let me just do this first. So let's take tau again. Take r equal to tangent rho some other coordinates. and r from 0 to infinity, then rho would be from 0 to 2 pi, pi over 2. Okay? 0 pi over 2. And you plug this into here with a little bit tiny. So after 2 seconds, you find the following metric. Okay. So this is easy to see because 1 plus tangent rho square is just 1 over cosine square, and etc. So the reason this metric is nice, because other than this conformal factor, this thing we can easily recognize. So this is just a cylinder. So this is just a cylinder. And let me draw it here. So this is a cylinder. Okay. So this direction can be considered the radial direction is the rho direction, and the circular direction, and this direction is the tau direction, and this direction is the omega d minus 1, or the polar coordinate direction. I'm only drawing one of them. Okay. So essentially, this have a structure of a cylinder. And at the center here, I have rho equal to 0. And here, I have rho equal to pi over 2. Okay? To go rho from 0 to pi over 2. Okay? And when you go to pi over 2, this cosine factor goes to 0. So the overall scale blows up. So here is your boundary. So pi over 2, yeah. So pi over 2 is the boundary. Okay. Is this clear? The pi over 2 is the boundary. Now the boundary map. So the boundary of the cylinder. So the boundary now is sitting at rho equal to pi over 2, has the topology of R times SD minus 1. Okay? So the boundary itself is a cylinder. So the boundary itself is a cylinder. The whole space is a solid cylinder. It's a field cylinder. Okay? But the scale factor blows up when you approach the boundary because of this prefactor. And the R is the time, and the SD minus 1 is the. So let's now, to visualize this space a little bit more better, let's look at the cross section. So imagine you put a plane in this space, okay? So now imagine, now let me call this this circular direction. Let's call it theta, and then now let's consider the cross section across this solid cylinder. So then we just have a plane. Okay, a plane. I should not have. Let's consider this cross section. Okay, in the center of this cylinder, I cut half. Cylinder cut it in half. So for example, in this notation, so this will be rho equal to 0. So here is rho equal to pi over 2. And I introduce this angular coordinate. So that will correspond to theta equal to 0. And here will be, again, rho equal to pi over 2, but theta equal to pi. Okay? And again, this is the tau direction. Is it clear what I'm doing? I cut the cylinder in half, and that's that cross section. So now, because of this structure of this times a conformal factor overall a scale factor, so the propagation of a light ray does not depend on this overall factor. The propagation of light ray can be seen from here. Okay? So now let's consider radial light ray, which only goes into the rho direction. Say so there's no in this angular direction. Let's consider the radial light ray. Then from that picture, it's very clear. So let's say this is tau equal to 0. Then it actually takes only pi over 2 for light ray to reach the boundary. Okay, because the rho only goes from pi over 2, and light ray always travel in 45 degrees. So this is just like, if you look at the minus tau plus the rho square, this is just Minkowski. And so light ray travel 45 degree. And then you reach the boundary, and then take another pi over 2. Yeah, so this is pi over 2. So this is tau equal to 0, and then this will be tau equal to pi over 2. Then suppose you put some reflecting wall here. Then by the time tau equal to pi, it has bounced back. Okay? And now if you go another round, then after at tau equal to 2 pi, then precisely go back to the origin. Then you go through a period. Okay? And that actually precisely is that the tau equal to 2 pi, which you define the angular coordinates. Yeah, if you follow that, then that corresponds to precisely one period of the light ray traveling in this. Okay? But the key thing is that the light ray will travel pi over 2 to the boundary. And now you can check, if you look at not the light ray, so light ray travels along the light-like geodesics. But if you look at the time-like geodesic, which is traveled by a massive particle, then you can show that the massive particle never reach the boundary. It will go into a motion like this. Okay? So this is a massive particle. So the massive particle will never reach the boundary. Will always be reflected back intuitively from the gravity potential. Okay, so you will show this fact yourself in your P set, show that actually the massive particle will never reach the boundary. So in the sense, so if you look at this metric at rho equal to 0, at rho equal to 0, this is essentially like a flat metric, because at rho equal to 0, this is just a sphere. So this becomes 1. This is a sphere. Yeah, the rho equal to 0, this is just like a Euclidean space, because this sine rho square becomes rho square. Okay, so this just becomes like a Euclidean space in polar coordinates, and then you have a time, and then this scale factor becomes 1. So at rho equal to 0, just like you have ordinary Minkowski space-time, and then the curvature comes in when you go to finite rho, and then those factors become important. And then you can show, just because of that, you can show that the massive particle will never actually travel to the boundary. Okay, always reflected back. In some sense, you can think of that the massive particle is always pulled back by the gravitational potential. Okay, pulled back by gravitational potential. So from a different point of view, is that another way to say it is a familiar statement which people often make, and often can give you great intuition, physical intuition, in many physical problems, is that ADS is like a confining box. just like a box. So things cannot escape from it. Okay. Okay. And in particular, the typical curvature radius is r. So you can roughly imagine this, because in the center it's like a flat space. So it's more like a box of size r. Okay, it's roughly. You can heuristic think of it as a box of size r.
Yes. Does it have finite or infinite volume? This is a finite or infinite volume?
Yeah,
infinite volume. It's infinite volume. Yeah.
Yeah, but because it's confining, most of the particles will only see the size r.
So one other question. So is it correct to say that it's like an anti-harmonic trap? If I'm in this space and I throw a ball out, it's going to come and hit me back in the head or something like that. Like, it seems like
Right. Yeah. We'll bounce back. Yeah. Actually, our own friend, Frank Wilczek, in the 80s, have tried to use this ADS, this feature, to say maybe this actually it describes confinement. Because if you put a quark there, they're confined. Anyway, yeah, but keep this heuristic picture in mind, because many physical problems actually, if you think in terms of this picture, become very intuitive. Okay. Okay. And often, so you say this is an exception for the light ray, but often we.
طبعا سمعتم الكلام الذي ذكره أن ويكزر هي اسمه من؟ نرجع مرة أخرى.
Impose the refracting boundary condition on the light ray, and for the light ray, this is also like a problem. Actually, actually, our own friend, Frank Wilczek, in the 80s, have tried to use this ADS, this feature, to say maybe this actually it describes confinement.
ويلشك استخدم مفهوم الكونفاينمنت في انه الكوارك اذا حاولت ان تفصل كواركين من بعض فانك ستنشئ او هذا الفصل سيؤدي الى خلق كواركين انتي كوارك اخرين ليرتبط مع الكواركات التي أنت فصلتها. هذا ما يسمى بالكونفاينمنت. وبالتالي هذا أيضا تستطيع تفسيره نظريتي. كيف تفسره؟ الأمر بسيط. أنت داخل الثقب الأسود الكتلة تضعف، أنت خارج من الثقب الأسود الكتلة تتضخم. طيب كتلة تضخمت ماذا يعني؟ يعني أنت أبعدت الكواركات من بعض، فهذا يعني زدت المسافة وكأنك خارج من الثقب الأسود الكتلة تضخمت. ماذا يعني تضخمت هذه الكتلة؟ هذا يعني تأثيرها سيكون كبيرا. طيب ماذا يعني تأثيرها سيكون كبيرا؟ هذا يعني أن الطاقة ستزيد كلما أنت أبعدت الكواركات من بعضها البعض، لأن الكتلة زادت. طيب ماذا يعني الكتلة زادت والطاقة تزيد؟ هذا يعني أنه إذا زادت الطاقة، إذا زادت الكتلة زادت الطاقة، زاد الهاملتونيان، والهاملتونيان زيادة الهاملتونيان أو زيادة الجرافيتي، خلينا نقول الجرافيتي أحسن، زيادة الجرافيتي يؤدي إلى زيادة الفاكيوم إنرجي، وزيادة الفاكيوم إنرجي يعني خلق كتل جديدة أو زيادة الفلكشويشنز للفاكيوم إنرجي، وبالتالي تخرج هذه زيادة الفلكشويشنز تخرج كتل أخرى، فبالتالي الكوارك يخرج كوارك آخر. هذا هو مفهوم الكونفاينمنت. بعدت الكواركين من بعض فإنهم كل كوارك ينفصل من الآخر يخلق كوارك آخر. نظرية ترجمته بكل سهولة، ويمكنه أخذ الترجمة أيضا من كتاب الحلقة 50 أنه إذا بعدنا من النواة ونحن طالعين خلال الذرة إلى المدارات الخارجية فإن الكتلة تتضخم والطاقة تقل، والعكس صحيح، الطاقة تزيد إذا نحن داخلين إلى الكتلة إلى كتلة الذرة، الطاقة تزيد والكتلة تقل. طيب بسبب أن داخلين الجاذبية، وبالتالي إذا زادت الكتلة زادت الطاقة في بالنسبة للconfinement، بالنسبة لل أو إذا نقصت نحن داخلين من الفضاء الكثيف أو طالعين من الفضاء الكثيف إلى الفضاء العادي، فإن الكتلة تزيد. زادت الكتلة ستزيد معها القوة الكهرومغناطيسية، وبالتالي يزيد معها quantum fluctuations، ويؤدي إلى ظهور كتل أخرى بزيادة quantum fluctuations. إذن ما فسره هذا العالم أيضا تفسره نظريتي بكل سهولة.
Because if you put the quark there, they're confined. Anyway, yeah, but keep this heuristic picture in mind, because many physical problems actually, if you think in terms of this picture, become very intuitive. Okay. Okay, and often, so you say this is an exception for the light ray, but often we impose the refracting boundary condition on the light ray, and for the light ray, this is also like a box, and you go to the boundary and you bounce back, actually. Okay. So now let me again just say it, but you should go back to check yourself. Now by looking at the relation between here, so here is a specific relation between R and X, and here is a specific relation between this X and this tau and this R. You can find the relation between this Poincare coordinate and this global coordinate. Okay, use a little bit of effort, and then you can show yourself. Let me just draw the picture. Again, let me use in the same picture. You can show that the Poincare patch cover a wedge, say at least in this cross section. The Poincare patch cover a cross section of this global ADS. Okay, so here is tau equal to minus pi, and here is tau equal to plus pi, and here say tau equal to 0. And in this Poincare patch, and then this line become R equal to 0, and T equal to minus infinity, and this line become R equal to 0, and T plus infinity. Okay, plus infinity. And so the time essentially goes around like this. Time goes around like this, and this line corresponding to T equal to 0. Okay, so T equal to 0 and tau equal to 0 coincides, and then you go to minus infinity rotating to that. So and the constant R surface. So this is a constant R surface in the Poincare coordinates. Goes like this, so the time goes up. Okay, and you can check yourself just by working out the relation between those coordinates through the x.
You mean this is wrapped on the cylinder?
No. I'm just saying.
Which picture? This is this picture?
Just within this cross section, I can look at this cross section. I see how this translates into Poincare coordinates, and that's what's happening. A Poincare coordinate cover this part. Okay. Okay, cover this part. I can also draw a more fancy picture here. Then roughly, what you can show is that in this general picture, is that the Poincare patch covers something like this. Okay, and the region between these two lines. So this is the spatial infinity of the in this Poincare patch. The boundary is Minkowski spacetime. So you see, so the Poincare patch cover like that, and then this is a spatial infinity of the Minkowski spacetime. This is the time infinity and time path of the Minkowski spacetime. Okay, so I urge you to do it yourself, because this kind of thing you really have to work through yourself to to have intuitive feeling for it. But this is a picture. Once you work out yourself, you compare with my picture, and then you will understand. Okay? So I will stop here today. Hence, one more sentence. This extended ADS contain infinite copies of this punctular patch. Okay?
The following
So D plus one dimensional ADS anti-de-Sitter space-time. So I assume all of you are familiar with the concept called isometry. If not, it's very easy to understand. So isometry refers to the class of coordinate transformations which leaves the metric invariant. Okay, and if it's if it's a Minkowski space-time, then the isometry would be the Lorentz transformation plus the translations. Okay, so that's the isometries. And for this ADS, by definition, the isometry would be SO d comma 2, because this is hyperbolic for ADS, because the ADS is defined as a hyperboloid in this d plus 2 dimensional Minkowski space-time with signature 2 comma d, and this preserves the Lorentz, this hyperboloid preserves the Lorentz transformation. So so the ADS, the symmetry would be SO d comma 2, just the Lorentz symmetry of this embedded Minkowski space-time. There's no translation because this equation breaks the translation. Okay? Because this equation breaks the translation. So yeah, so you can see it immediately just from there. But what we will be useful later is to understand how this is reflected in the so-called punctular patch. Okay? So let's talk about how this symmetry is realized in the punctular patch. Which I will use these z coordinates. So first,
طبعا ما فيها translation symmetry لأنه أي حركة أو التقسيمات الزمنية أو السلايسز في الفضاء تغير الحركة. يعني مثلا نحن نعلم أنه على سطح الأرض أو الجسم الساقط على سطح الأرض حركته تزيد، الطاقة الحركية تزيد من الأعلى وهو قادم نحو الأسفل. فالسبب أنه هناك دوائر حول الأرض من الزمن، تايم يقال عليها تايم كونتراكشن. كل ما يعني بينزل الملاحظ الموجود على سطح الأرض يرى الجسيمات الواقعة ساقطة على الأرض، فإن طاقتها تزيد، الطاقة الحركية. الحساب طبعا طاقة الوضع. زيادة الطاقة الحركية هذه يجب أن تسبب البريكر أوف ترانسليشن سيمتري، لأنه الزمن كما قلت في الفضاء كما قلت مقسم حول الأرض، بحيث أنه كلما تقارب الجسم من السطح كلما زاد التايم كونتراكشن والسبيس كونتراكشن. طبعا درجة بسيطة جدا لأنه كتلة الأرض ليست كبيرة. الأمر ينطبق أيضا داخل الثقب الأسود، وينطبق أيضا في فضاء ADS، أيضا ينطبق هذا الأمر. لكن فضاء ADS يختلف عن الثقب الأسود في شيء، لأن الحركة تقل لأنه فضاء ADS ليس فيه جاذبية، الحركة تقل. جميل.
of you are familiar with the concept called isometry would be the Lorentz transformation plus the translations. Okay, so that's the isometries. And for this ADS, by definition, the isometry would be SO d comma 2, because this is hyperbolic for ADS, because the ADS is defined as a hyperboloid in this d plus 2 dimensional Minkowski spacetime with signature 2 comma d, and this preserves.
أقصد تزيد مثل الصبرات لا تنقص، تزيد، لأنه أصلا الفضاء أصلا منحني. فضاء الإيديس فضاء منحني بالمناسبة. نعم، فهي تزيد مع زيادة الطاقة الحركية، تزيد مع زيادة كلما تعرضنا إلى نحو تعرضنا يعني في الفضاء عمودي في الفضاء من الباوندريز إلى الداخل، فإن الطاقة الحركية تزيد. طبعا بالتالي تضعف طاقة الوضع. طاقة الوضع هي طاقة الجسيمات والنسبية الخاصة، السيمتري، النسبية الخاصة E يساوي MC سكوير. طبعا هي هذا سيمتري لها علاقة بلورينز سيمتري، فهذه تضعف، الكتلة تضعف، القوة الكهرومغناطيسية أيضا تضعف، وهكذا كما مثل ما يحصل في الثقب الأسود.
The Lorentz, this hyperboloid preserves the Lorentz transformation. So the ADS, the symmetry will be SO d comma 2. Just the Lorentz symmetry of this embedded Minkowski spacetime. There's no translation because this equation breaks the translation. Okay? Because this equation breaks the translation. So so you can see it immediately just from there. But what we will be useful later is to understand how this is reflected in the so-called Poincare patch. Okay? So let's talk about how this symmetry is realized in the Poincare patch. Which I will use these z coordinates. So first, there are translations, which we can translate, say, x mu to some constant. So by x mu, I always refer to, using these Poincare coordinates, the x mu, I always refer to t and the vector x. Okay? So this is the. So first, obviously, there's a translation in the t and x direction because nothing depends on t and x. And then there's also Lorentz transformation in the x direction. Because the dependence on the t and x is just a Minkowski metric, because each is foliated by a Minkowski metric. Okay? So this has d generators. So these have 1/2 d times d minus 1, because this is the Lorentz transformation in the d dimension. And then also there's a scaling. So that metric is invariant under such a scaling. So if you scale x mu and z together, then clearly the metric does not change. So if you scale z and x together, then all this scaling cancels. Then of course this does not change the metric. Okay? So there's also scaling. So these have one generator.
طبعا
So the last isometry.
طبعا السكيلين هو قال اكس وزي الاثنان يزيدان مع بعض. اكس وزي يعطينا ماذا؟ زيادة المترية وزيادة العمق نحو نحو المركز. يعني زي طبعا عكس ار زيادة ار يعطينا العمق نحو المركز، الشكل اللي هو الشكل الاسطواني للاي دي اس. اما زيادة يعني يعطينا هي طبعا مقلوب ار، وبالتالي يعطينا ار يساوي 0، ومفترض عند ار يساوي 0 فإن المترية دي اس يساوي 0، وعند ار تساوي لا نهائية أو فإن الدي اس يساوي لا نهائي. بالتالي إذا زدت الزي يعني نقص ار، لكن هنا علينا نزيد الاكس اللي هو اكس هي السبيشال متريك في المترية، فبالتالي نقص ار من اجل الدي اس لا يساوي لا يصل الى 0 فانك تزيد الاكس، فبالتالي تكون الدي اس ثابتة. الدي اس سكوير نتحدث عن المترية ونتحدث عن الجيومتري. هذه الذي تتفق في ماذا؟ تتفق في أنه إذا زدت إذا نقص الآر والدي اس تنقص، فهذا يعني الجسيمات حجمها ينقص، لكن إذا زدت الدي اكس فإن الجسيمات يكون حجمها ثابت. نقصان الجسيمات بالمناسبة هي تكسر سيمتري، حجم الجسيمات المتفاعلة أو موضع الدراسة تكسر السيمتري، لأنه الدي اس إذا نقصت فإن حجم الجسيمات تنقص، وبالتالي الفيزياء تتغير. لكن إذا أردت سيمتري ثابت فإنك نقصت ار فإن مفترض أن تنقص الإكس، وإذا زدت ار يجب عليك أن تزيد الإكس، وهكذا. هذا يسمى بالسكيلينج.
In the it's called spatial conformal transformation. The last symmetry of this space, which is called the spatial conformal transformation, is a little bit more complicated. Let me just first write it down, then I will try to give you some intuition about it. So the free parameter, so the parameter for this transformation are a vector b mu. Okay, so I will introduce. So the transformation is the following: z equal to z prime equal to and x mu goes to x mu prime okay. So b mu is just an arbitrary constant vector, just constant vector. And this a so b mu square, so b square is just the standard b mu. And the a square is defined to be z square plus x mu. Okay.
انظر إلى هذا السيمتري غريب جدا. Special conformation transformation. Conformal special conformal transformation. هذا السيمتري غريب جدا جدا، وهذا السيمتري يصف تحديدا اتفاق مع نظرية في موضوع داخل الثقب الأسود، لأنه فيه فيه زد، فالزد يعمل على كالآتي: الزد عندما يكون 0 هذا يعني ار يكون ما لا نهاية، وار ما لا نهاية. ماذا يعني ار ما لا نهاية؟ طيب تعالوا نشوف الصورة. الصورة لم أجدها، لكن يمكنكم تخيلها. تخيلوا أنه رسمة البلين، عندما رسم البلين وبعد البلين عمل ثروت أو نفق إلى تحت، فالبلين هو عبارة عن R6 والثروت عبارة عن R5 اللي يمثل الكلوز سترينج. وتحت السترينج هناك خصوصا في المترية، أنا أتحدث عن المترية، في تحت الثروت أو النفق تحته هناك تعتبر المترية الخاصة R سكوير دي أوميجا 5 أو دي فضاء 5 أبعاد. وفيها في تلك المنطقة الصغيرة فيها البرين، والبرين قال يختفي بسبب انه هو دي 3 والفضاء دي 5، ويظهر فقط من البرين يظهر الفلوكس. هذا الطول كله هو طول R سمول وليس R كابيتال كونستانت، لكن هذا الطول كله هو R سمول. فهذه الR عندما تكون ما لا نهاية، هذا يعني ماذا؟ هذا يعني أن زي تكون 0، وعندما R تكون 0 زي تكون ما لا نهاية. طيب، فما يحدث إن عندما تكون R ما لا نهاية كما قلنا أنه عبارة عن DS يكون ما لا نهاية، يعني الفضاء يكون ما لا نهاية. وإذا R أصبح 0 فإن DS يساوي 0. هذا طبعا ينعكس على الجسيمات. إذا R ما لا نهاية الجسيمات تكون صغيرة جدا جدا، وإذا R 0 الجسيمات تكون ضخمة جدا جدا. الجسيمات أنا أقصد بها السترينج طبعا، أو أقصد بها البرين. طيب، نجد هنا أن Z تتناسب عكسيا مع R. فهذه المعادلة الغريبة تخبرنا بهذا الأمر، أن Z تؤثر تأثيرا مباشرا على الجسيمات أو على البرين. Z 0 يعني الفضاء كبير جدا جدا، وبالتالي الجسيمات لا تظهر منها شيء، أو البرين لا يظهر منه شيء عدا الفلوكس. إذا Z ما لا نهاية إذن البرين صغير جدا، الفضاء صغير جدا، بالتالي يظهر خصائص البرين كاملة بما يحدث الديفكت لهذا الفضاء. هذه التركيبة الغريبة جدا هي ما تؤدي لنظرية يوسف. طبعا لا يعني حتى الآن لا أستطيع أن أعينها هنا بكل وضوح، يعني يعرفكم يقولوا البي يساوي كذا، الإكس معروف لكن البي والإيه لا أعرف. لكن إذا بحثت في هذه المعادلات معادلتين ستجدون نظريتي صحيحة وكلامي هذا صحيح. في هذه المعادلات تؤثر مباشرة على البرينز، تؤثر مباشرة على الجسيم الصاغط داخل الثقب الأسود، وتتفق تماما مع الجسيم الصاغط داخل الثقب الأسود. لهذا أنا طبعا هعمل لها سكرين لأن هي مدعاة للبحث. هي مدعاة للبحث فهعمل لها سكرين. انظر هنا 3 معادلات، زي برايم والاكس برايم بدلالة الاكس، ولدينا الاي 4، ولدينا البي 4 معادلات. البي يساوي بي ميو وهو سكيلر، والاي تربيع يساوي زد تربيع زائد اكس ميو يعني سكيلر مع زد تربيع على زد طبعا هو المقياس. فهذه المعادلة معادلة معقدة جدا جدا، تصف تماما إذا بحثت عنها وحاولت أن تفندوها وتحللوها ستجدوها تصف تماما الفضاء في في نظرية فضاء داخل الثقب الأسود، حيث أنه كل ما تعمق الجسيم أو نقول البرين، كل ما تعمق البرين عميقا داخل الثقب الأسود فإنه حجمه يصغر. هذا هو تعبير به هذه المعادلات. طيب تعالوا نستمر.
Requires a little bit of effort. You plug this transformation into this expression, and then you can show that this is invariant. Okay, so these have d parameters because b. So the so the transformation parameters, they're the d parameters. So they're d parameters here. Okay, because of the b mu. So this transformation can be understood in a slightly easier way as follows. It's as you will also do this in your P set, is that you can check. So to understand this special conformal transformation, so I call it SCT. First, you can check the following is isometry, something we call the inversion. Is that if z goes to z divided by a, so a is this quantity, or a. I think I'm having some notation error myself. So I should call it a rather a squared. So sorry, doesn't matter. I can also call it a squared, but let me just call it a. I think that one would be a2. Yeah, that is a2. So yeah, I could just call everything a squared, but to be consistent with my notation on the loads, just let me call it a. So you can also check that the following discrete transformation is also isometry. So when z goes to z divided by a, and x mu goes to x mu divided by a. Okay? You can check this is isometry. So if you plug this into this metric, you find this leaves the metric invariant. And this thing is much easier to check. But as you will do in your P set, and you can check yourself, this discrete transformation actually is not part of the SO d comma 2. It's in fact part of the O d comma 2. So if you calculate its determinant, say the Jacobian, actually you find the -1 rather than 1. Okay? So this is not a proper Lorentz transformation. It's not a proper transformation, what we normally call proper transformation. But however, you can do however, if you do this twice, then -1 times -1 equal to 1, then you get the proper transformation. But of course, if you do this twice, you just go back to itself. You can check this is inverse of itself. So this is like a Z2 transformation. But you can do a slightly trick. Then you can show that this you can show that this special conformal transformation is given by an inversion. You first do an inversion, and then you followed by a translation in B mu, and then you invert it back. Okay? So even though you can check that I square is equal to 1, but now in the middle you have added the translation in B mu, a constant. And this is a symmetry, and of course the whole thing will be a symmetry. But now this is a proper transformation because I have act I twice. Okay? So you can now check this transformation is precisely, if you do this, it's precisely just that transformation. Okay? So if you add all of them together, d 1/2 d minus 1 d, then you can show actually they form this symmetry group. Okay? They form this symmetry group. So all together, you have d plus 1/2 d times d minus 1 plus 1 plus d, then that gives you 1/2 d. You can check yourself that 1/2 d plus 1 and d plus 2, which is precisely the number generated for that one. Okay. Yes.
So the total here, the dimension is d plus 1.
Yeah.
Why, like even translation, it only has a d-dimensional invariant?
No, because this depends on z, so the translation in z is not invariant. Because this depends on z, so if you translate z, this is not the isometry, and the metric changes. So only the translation in t and x is a symmetry. So that's why we only do the translation x mu.
I have a question. So inversion is isometry.
Yeah.
Yes. Okay. So by inversion, as you said, it is not in the SO2.
Yeah. Right.
So that means the symmetry, isometry group is bigger than SO.
Yeah. It's the standard story. You have a O. You can have a O symmetry. There's a discrete part which is.
طبعا ذكر قبل قليل أن السيمتري الترانسليشن along z هو الذي يغير، لأنه هذا along z هذا يدخلنا في الثروت أو في النفق الذي ذكرته قبل قليل، لكن الترانسليشن في الاكس والواي فإنه لا يغير شيء، لأنه هو الترانسليشن في السطح لا يدخل في الثروت. في السطح لا يفعل شيء، لكن إذا دخلت في الثروت فإن الحجم سينقص، مثلما داخل الثقب الأسود. داخل الثقب الأسود نجد أن الزمكان يكون في شكل دوائر حول جسم الثقب الأسود، فأي حركة في هذه الدوائر أو الكريات، كرة جمع كرة، فهي حركة لا تؤثر على الجسيمات، لكن إذا انتقلنا عموديا نحو مركز الثقب فإن ذلك يؤثر على الجسيمات، مثل ما يعني اتفاق مباشر.
This when you transformation you change the Jacobian, whether the Jacobian is 1 or minus 1. It just has exactly the standard of the transformation in the Minkowski space-time. In Minkowski space-time, you can also consider such transformations. Yeah, just the same thing. Because this is just the transformation in the Minkowski space-time of this embedding space.
So in the embedding metric, we also have determine the minus 1 transformation.
Exactly the same as the standard Minkowski space.
But the discrete part just like parity.
No, it depends. In the order dimension, in the 3 plus 1 dimension, just the parity. That's right. In the 2 plus 1 dimension, if you invert all directions, then it's not. Right?
So,
Yes.
Is there an easy way to see the spatial conformal symmetry of the system? Is there an easy way to see the symmetry from the metric?
Yeah, you just plug this in.
Well, I mean, how do you know that there exists such symmetry, complicated symmetries?
No, let me just say another way to understand is to do this one. So this inversion is a much simpler transformation, which you can easily check its isometry, and then this procedure will guarantee this is isometry, because each step is isometry. Good. Okay, so after talking about so that concludes our very quick review about the geometry and the properties of anti-de Sitter space-time.
Maybe one more quick question. So since you said the isometry is bigger than SOD2, why you only concern on the SOD?
No, it's the same thing. In Minkowski space, we can also separate the discrete transformations and consider the continuous part. It's just exactly the same thing. Yeah. Certainly here we can consider the inversion too. It just here I'm considering the part which connect to the identity. Any other question?
So is it true that in some dimensions the inversion is also isometry?
I think no. I think actually in all dimensions this is not. In all dimensions this is inversion is always isometry. In any dimension. No, it's always -1 in any dimension. Yeah. Other questions? Good. So after talk about the anti-de Sitter space-time, now we can talk a little bit about the string theory in anti-de Sitter space-time.